Hi there. So in this video, we're going to look at the chain rule. The chain rule is something you studied in single variable calculus, but we need to talk about how it works for functions of several variables. And just to remind you, the context in which the chain rule applies is where we have a function composed with another function. Right? So we have one function plugged into another function, and we want to differentiate that. And so that's the situation that we're seeing here. We've got a function of x and y, and each of x and y are functions of t. Now in single variable calculus, you would have only seen one of these, right? But now we have multivariable functions, so we can have more than one. All right, so let's look at this case first, where we have one independent variable, this t in here. What does the chain rule say? Well, it says that if I want to differentiate z, so if I want to compute the derivative of z with respect to t, then what I'm going to do is I'm going to first differentiate z with respect to x, and then x with respect to t. But then I also have to consider the y. So I also have to differentiate z with respect to y, and then y with respect to t. And the way we combine all these is as follows. Now, notice that I wrote the d's differently, depending on what part I'm writing them in. And there's a reason for that. This is a partial derivative, the curly d. The reason I'm using a partial derivative is because z is a function of two variables. Z is a function of x and y. So whenever we take a partial derivative, we use the curly d. However, x is a function of only one variable. Same with y. So when I'm differentiating x or y, I'm going to use the straight normal d. So that's the distinction that you should make. And when you write these down, you should be doing the same thing. If it's a function of several variables and you're only differentiating with respect to one of them, use the curly d. If it's a function of only one variable, you use the straight d. And this is the chain rule. Now, it looks a little bit messy, but it's really not that bad once you get the hang of it. You know, when we're differentiating z, you first differentiate z with respect to the first variable, and then you multiply it by the derivative with respect to the second variable. But since there's more than one variable, we do that for each, and then we add them together. Now, to keep things straight, just as a reminder to make sure you did them right, if you just treat these as fractions, which they technically aren't quite, they're limits, and so they don't always work like fractions. But in this case, it's a good rule of thumb you can kind of look at to use. If you imagined you could cross these out, then what you're left with is dz dt, which is exactly what we have on the left-hand side. So that tells me I did it right. And again, these are the same, so if I imagined crossing them out, I get dz dt. So make sure that it works that way, and then you'll know you have it right. Okay, so that's for the first case here. Now let's look at the second case, where we have two independent variables, u and v. Okay, so there are two possible derivatives I can differentiate z with respect to. Z could be differentiated with respect to u or v. Okay, I'm just going to start with u. We'll do v next, but let's just do one at a time. So the partial derivative of z with respect to u, notice what we've done here. We've just differentiated z with respect to x, and then x with respect to u, and then z with respect to y, and then y with respect to u. It's very similar to what we did above. So note again that if I were to cancel these, which technically you can't do, but this is a kind of a rule of thumb, I have dz du just like on the left-hand side. And if I were to cancel these, I would have dz du. So that's how I know I've lined things up correctly. Okay, that was dz du. Now let's do dz dv. Notice that this is almost the same, except I've just, instead of differentiating the x's and y's with respect to u's, I'm now differentiating with respect to v's. But otherwise, it's exactly the same as what we did up here. So that's how the chain rule works. Now, if there were a third variable, u, v, w, well, I could take a third derivative here. And there'd be another, I could write down another row of computations to explain how that works. But I think you can see how it would go. Now, I also want to point out a distinction between these and this. Perhaps you saw it. I didn't use the straight d down here. I used the curly d. Why is that? Well, because whereas this one was an ordinary derivative with respect to a single variable. These are partial derivatives. So because these functions x and y are functions of two variables, I use the curly d to denote it. So that's why we have that distinction between these two formulations. All right, so I want to look at a series of examples. The first example that we're going to look at is this one, and it's going to be an application. All of these will be applications of the chain rule. So it says, at a museum, tickets for adults cost $15 and tickets for children cost $5. The number of adults and children visiting the museum varies throughout the week. So part A says to use the chain rule to find the rate at which the revenue generated from ticket sales changes with respect to time. Okay, so let's write down how we would compute the revenue. Let's call it R. Well, it's $15 per adult, so it'll be 15A, where A represents the number of adults, plus $5 for every child, so $5 times the number of children. Okay, now I want to differentiate this with respect to T. So the number of adults and children varies throughout the week. So that means that A and C are functions of T. So keep that in mind when we do this. So if I want to compute the derivative of the revenue with respect to time, well, I will first take the derivative of the revenue with respect to A, and then multiply by dA dt, and then take the derivative of the revenue with respect to C, and multiply by dC dt. And let's see what we get here. Well, dr dA. Well, I treat C as a constant, so when I differentiate, I just get 15. And then I have dA dt. I think we can just write A prime here. dr dC, well, I treat A as a constant, so that's gone. I just get 5. dC dt. Okay, so that's part A. Part B, if adult attendance is decreasing at a rate of 7 people per day, and child attendance is increasing at a rate of 10 people per day, then how is the revenue changing? Well, what they're telling us here in part B is that A prime is decreasing at a rate of 7 per day, so that's -7. And C prime is C is increasing at a rate of 10 per day, so that's +10. And so I can see from this that dr dt, therefore, is 15 times -7 plus 5 times 10, which is, let's see, that's -105 plus 50, so that's -55. We might want to put some units here. The revenue is changing. That is dollars per day. All right, in this next example, we have, let's see, positions x and y are parameterized according to the following parameterization. So x and y depend on other parameters u and v. How does the height of the graph, given by this, change with respect to u? All right, so z is a function of x and y are functions of u and v. So this is a situation where the chain rule is applicable. So if I want to find the rate of change of z with respect to u, I'm looking at dz du. Well, we know that dz du is dz dx dx du plus dz dy dy du. That's the chain rule. Notice that if I were to pretend to cancel these, what I get on the right-hand side matches what's on the left. So I know I set it up right. Okay. What's dz dx? Well, that would be -2 e to the y minus 2x. What's dx du? Well, the derivative here is 3. So multiply by 3. What's dz dy? Well, that's just e to the y minus 2x. And what is dy du? Well, that's just 1. All right, well, I can simplify this a little bit. This is just negative 5 e to the y minus 2x. Now, notice they're asking how does it change with respect to u. They probably want the answer in terms of u and v, because they've gone down to that level. So let's write the answer in terms of u and v. So let's see, y is u minus 2v, and x is 3u plus v. So we now just simplify this, and there is our final answer. Okay, here's our last example. Implicit differentiation. We want to compute dz dx given this equation, all right? And it says here y does not depend on x, all right? And that means that the derivative of y with respect to x will be 0. So in other words, x and y are free variables. Neither one depends on the other. Let me show you what's going on here. This equation, if you graph it, will look something like this. All right, so it now the computer software here is not being 100% correct. It's actually merging these parts together. This flat surface and this curved surface in reality are not connected, and so this bridge over here should not be there. Same thing on the bottom. There's a little bit of a bridge it's putting here. It shouldn't be there. So the computer's not perfect, but it's giving us a kind of an idea of what's going on here. So it's got, the graph consists of 3 different pieces. It's got this flat plane over here, and then it's got this upper curvy piece, and then this down bottom curvy piece. All right, and so x and y are free variables. Neither one depends on the other. I'm free to choose either one of them however I want. Okay, and that's what they were saying. Y doesn't depend on x, but z depends on x and y. As you can see, depending on where I put x and y, z could either be on this flat surface up here or down here. Okay, so we want to compute dz dx. Okay, well, here in this one, I think you'll have a hard time trying to solve this for z, but that's okay. And if you can't solve an equation for a variable, you can still use implicit differentiation to find the derivatives. So we'll just go ahead and just differentiate everything with respect to x to find the derivatives. All right, so let's go through this. So I'm going to take that whole thing and just differentiate with respect to x. So d by dx of the left-hand side equals d by dx of the right-hand side. Well, the right-hand side is, of course, just going to be 0, but the left-hand side's got stuff for us to work with here. So I'm going to first differentiate this. All right, so we have a product, so we're going to use the product rule. So the derivative of x with respect to x, well, that's just 1. And then I have x times the derivative of this with respect to x. All right, so we're going to differentiate this. Now, if I differentiate this, the exponent comes down, 2 times z. And then z depends on x and y. We saw that in the picture, right? Depending on x and y, where the graph looks different, right? So z does depend on x and y, so we will multiply that by dz dx. Now that's the chain rule. We differentiated this function with respect to z. That's this piece. This is that function with respect to z, and then we are multiplying it by dz dx. That's the chain rule. Okay, then we go to the next part. We're differentiating this with respect to x. Well, like we said, that depends on x, so dz dx, right? And then that part doesn't depend on x, so we just leave it, right? And on the right-hand side, we have 0. And so this is what we're getting here. So what I'm going to do is this is just z squared. I'm going to subtract it from both sides, and then I'm going to factor out dz dx from these two terms. Okay, so let's do that factoring, and I'll move that thing to the other side in the next step. Okay, so we'll just factor out dz dx. So we got dz dx times 2xz minus e to the y. And then, like I said, I'm going to subtract z squared from both sides, so it'll end up over here. And then, because I'm solving for dz dx, I'll just divide both sides by this stuff. And there we go. We have an expression for dz dx right here. So if you wanted to know the rate at which the function z was changing in the x direction at any point x, y, z on the graph, you just plug those coordinates x, y, z into this expression, and this would give you exactly that.